Recording in progress.
Okay, welcome. Welcome to lecture 2, week 7. Can you hear me okay? Perfect. Thank you. So let me go right away and get some notes for us at once. Let me see. There. There. And let me see. There. Lecture 2, week 7, Math 2305, Spring 2025. So let me see, I'll run through the syllabus, but we need to take a look at the pigeonhole principle. That's something that we use in computer science for counting, and a method of proofs for mathematicians. So it started as a method of proofs, but it's a method of counting also. So it's in section 9.4 in Susana's textbook, but it could have been in chapter 4 as a method of proof. So before I do that one, let me do just one proof. Let's say we do this one. Let me see. Right there. We can do if show or proof. Proof that if A is an integer, is in Z, such that, let me admit more students. Prove that if A is in Z, such that A it's equivalent to 1 mod 5. Then A square, let me write it better. A square is, boom, A square. It's strange. It's telling me that there are 4 students waiting, but it's always 1 student waiting. And I've done that for the 10th time. It's not, and now, let me see, it's 1 student at a time is showing up. It's equivalent to 1 mod 5. Right there. Okay, let me see there. Let me stop sharing and see all the students that they could potentially be waiting. No, only 1 student there. Okay, so they could have written this like this. There for all A in Z, comma. I don't see any student waiting, but it's telling me, okay, for all A in Z, if A it's equivalent to 1 mod 5, then A square it's equivalent to 1 mod 5. and close the brackets. So I could have potentially written it that way, as a universal conditional, right there. It's equivalent to what is written right here. These two forms are the same. There. And there. Perfect. So let's go for it. Solution. Oh, solution. I've been doing too many problems in calculus. Proof. Right there. Assume the hypothesis. So assume A is in Z and A it's equivalent to 1 mod 5.
I think that something's broken because someone in the group chat is saying that they didn't get let in.
Let me check at once. Thank you, Ansley. I'll go at once. It keeps showing me that 4 students want to come in. When I go there to try to let students in, is nobody there. Let me view again. I'm going for the view. Yeah, I'll check again. Oh, I'll check again. Yeah, now I can see 3 students. Yeah, just now. But it's saying that there are 4. Okay, now they're all in. Thank you, Ansley. Thank you. Let me see, and I'll share again. Yeah, when that happens, tell me. But they just showed up. So then I need to remember the definition right there. So by definition, 5 divides A minus 1. 5 divides A minus 1. So perfect. Let me go right there. By definition, five divides A minus 1 right there. And I'll let you keep going, and I'll just keep going on your own, and then I'll go back and finish it right there. Just feel the moment of loneliness. So we're practicing a little bit for the exam.
Do you mind scrolling up just a little bit?
My pleasure, my pleasure.
Thank you.
Yes. And let me put more volume so I can hear you better. There. Okay, let me see there. So let me see. By definition, we have that. So there exists K in Z such that A minus 1 it's equal to 5K right there. So there comes the moment where you know that we need to bring the A square right there, or yeah, or we can bring the A square minus 1 right there. So consider A square minus 1. We want to show that 5 divides A square minus 1 because comma, if you hear a phone in the background, it's my colleague's phone. He went to teach and his phone is right there making some music. So yeah. I'm gonna go and get the phone and put it inside a closet. 2 seconds. I covered the phone with a sweater. That's it. So perfect. Let me see. Yes, go ahead.
Oh no, sorry.
Okay, perfect. If you
Accident,
have
my
a
bad.
question, jump. So I want to show that 5 divides A square minus 1 because if 5 divides A square minus 1, then that means that A square minus 1 it's equivalent to 0 mod 5. Thus, A square it's equivalent to 1 mod 5 right there. I just I added 1 to both sides of that equivalency. So that's the plan. If I can show that 5 divides A square minus 1, I've done it right there. So, and I was explaining that, and I can put this in brackets right there. So perfect. And recall that A minus 1 is 5K. A minus 1 is equal to 5K. So we are almost done. I'm going to factor because that looks like the difference of squares. So by algebra, let me see. By algebra, we can see that A square minus 1 it's equal to A square minus 1 square, and that is equal to A minus 1, A plus 1. But that is equal to 5K A minus 1, which is equal to 5K A minus 1. Since K times A minus 1, it's an element of Z by closure, comma, we get that 5 divides A squared minus 1. Thus, A squared minus 1, it's equivalent to 0 mod 5. That is A squared, it's equivalent to 1 mod 5 as desired. And put a little box right there. Happiness with that?
Sorry, quick. I might have missed it. Where did you get the 5K from?
Up here.
Oh, I see it. I'm sorry.
Yes,
Yeah.
no problem. All the way at the beginning of the proof. Yeah, A minus 1 equals to 5K. Perfect. So that's it. This is a little bit of modular arithmetic. And then I need to give you a big theorem. Let me see. I'll put it right here. Theorem. Right there. The theorem says let for all A, comma, B, comma, and N in Z integers and N greater than 1. Right there. The following are equivalent. The following are equivalent. In math, for the following are equivalent, we write this. T, F, A, E. TFAE, and people will know that we mean the following are equivalent, because there are so many times that sometimes we need to write this for these big theorems that have lots of connections right there. So here they come. Here they come. The following are equivalent. One, N divides A minus B. Number 2, A, it's equivalent to B mod N. And of course, that one is an easy one. That's our definition. So that's fine. Number 3, A is equal to B plus Kn for some K. In Z. Number 4, A and B share the same remainder when divided by N. A and B have the same remainder non-negative remainder. And that's a little pedantic. Definitely is non-negative. We know that the remainder is trapped between 0 and below the divisor. We know that, but it's nice to put it there. So it's not pedantic. It's actually nice to say it. A and B have the same non-negative remainder. Right there, when divided by n. And last, number 5, A mod n, it's equal to B mod n. Can you see that we connected? We connected the mods with equivalency, the ones that have parentheses, way up there, number 2. We connected number 2 to number 5, right there, by this chain of equivalencies. This chain, the following are equivalent, so they're all the same, but we are usually always playing with the first 2. Improve. We are always playing with those first 2. So how do you prove something like this? The following are equivalent. You show that 1 implies 2, that 2 implies 3, that 3 implies 4, that 4 implies 5, and that 5 implies 1. Can you see what I'm saying? You go like a little, what are those type of parties that they hold from their waist and they all like do like a train? Is some I don't know what it's called, but
Conga line?
yeah, they do a conga line. So this is the conga line proof. I never thought of that, but that's what we can call it, the conga line proof. So we'll say that. So perfect. Proof. Yeah. We'll say it right there. We will show that 1 implies 2, that 2 implies 3, that 3 implies 4, 4 implies 5, and that 5 implies 1. And then you are done right there. So some of them are easy, some of them are more so how many this is a bunch of problems in one. Is 1, 2, 3, 4, 5 conditional statements right there. So let's go for it. Let's see how far we can take them right there. So perfect. Proof. Well, right there, I will go prove that 1 implies 2. Show one implies 2. This is the easy one. Suppose n divides a minus b. By definition, we know that this is the congruence, A equivalent to B mod n. So then I will say, by definition, we know, by definition of congruence modulo n, by definition of congruence modular n modulo n, we can immediately conclude. We can conclude that A it's equivalent to B mod n. That's the easy one right there. Next, proof from 2 to 3. Next, show two to three. That one is only one algebraic move. I'm thinking adding B on both sides. Let's check it out. So we're assuming number 2 and we want to get to number 3. We are going to use the definition of A equivalent to B mod n. So suppose A is equivalent to B mod n, comma, by definition, A divides, well, n divides A minus B. So A minus B it's equal to nk for some k in Z. There. By algebra, we add B to both sides. To get, and then that's it. We're playing with this equation. Add B to both sides. So we get A minus B plus B equal to B plus nk. A it's equal to B plus nk, and that's what we had to show right there. That was number 3. So we went from number 2 to number 3. Now this one is more involved. We have to go from number 3 to number 4 right there. So let's assume number 3 and then try to get to number 4. Okay. This one is more tricky. So we'll say it, show, and this one was show 3 to 4. Perfect. Show 3 to 4. Show 3 and get to 4. Right there. Let me take a look at the notation. Perfect. So right there, assume, right there, assume. So we assume 3. Assume A is equal to B plus Kn. For some K in Z. Right there. Okay. Keep in mind that okay, we have we are going to put A through the quotient remainder theorem. So we say take A and use the quotient remainder theorem. When you divide by n, use the quotient remainder theorem with divisor n. There, to get And we get that in full splendor. A, it's equal to Qn plus R, where R is trapped between 0 and n. R is trapped between 0 and n. So look what we have. A is equal to that. A is equal to this. Let me circle it. A is equal to this. A is equal to this. So I can set them up to each other to be able to solve for B. So this one was more involved. This one was more involved. I could have potentially gotten stuck on this proof. So this one is the one that we're using the quotient remainder theorem on A. So perfect. See that we have A equal to B plus Kn. And that is equal to Qn plus R. And then that's it. We'll do algebra on this. We'll solve for B. Right there on that. By algebra, B, it's equal to Qn plus R minus Kn. And this is equal to B equals to Q n minus K Q minus K n plus R right there. So now both A and B have the same remainder when divided by n right there. That I see the remainder right there. That's the same remainder as the one that is trapped between 0 and n right there. So above, so here is the, see that we have A equals to Q n plus R. And B equals to Q minus K n plus R. Thus, A and B have the same remainder. When divided by n. Right there. So that's it. Next, we would like to go from 4 to 5. 4 to 5. So we say here, show four implies 5. So assume A and B have the same remainder. When divided by n. Question? Okay. There. So we already have that notation. So R is right there. A, no parenthesis. R is A mod N, and R is B mod N by definition. The remainder, that's the notation that we have for the remainder. There. Thus, or hence, R it's equal to A mod N. That is, oh, I'll do this. Hence, A mod N it's equal to B mod N as desired. Right there. And comes the last one on this, let me see, show 5 implies 1. To finish the dance, to finish that dance. Happiness with that. There. So that last one right there, let me see. Let's take a look at there. So we can assume A mod N it's equal to B mod N. The remainders, the two remainders are the same. Right there. So by the quotient remainder theorem, uppercase, by the quotient remainder theorem, we can see that both, well, we can see that A it's equal to K and K plus R. For some K in Z. Right there. And B it's equal to NQ plus R for some Q. You have that equation. Subtract A minus B. You have that equation. Subtract A minus B. So by algebra, we get, and let's subtract A minus B. It's equal to NK plus R minus NQ plus R. And that is equal to nk minus nq plus r minus r. And that is equal to nk minus q. See that k minus q is in Z by closure. It's in Z by closure. Thus, n divides a minus b as desired. Right there. We did it. That's it. We went with 1 implies 2, 2 implies 3, 3 implies 4, 4 implies 5, 5 implies 1. Right there. So the most important out of this theorem, they're all equivalent, but the most important is 1 and 2. I'm utilizing those all the time for a lot of proofs. I never play with the other ones. I acknowledge the other ones, but I'm always playing with these two. Right there, with that definition. Right there. Happiness with that. So, okay, there. Oh, and then of course, let me just put a problem just to emphasize that, and then I'll just put a statement. So I'll say no. I always play with the top two. Right there. There. No. Not well. Right there. We always work. And my pen is running out, so I'm gonna run and get my other pen. We always work with, and it's always this. It's always A equivalent to B mod N means N divides A minus B. Right there. And then we can put a statement so that we believe that we are always doing that. We can write this one, example. Let for all A, B. Well, I'll run to get the pen. But what I want to write is A, it's equivalent to B mod N implies A square it's equivalent to B square mod N, just to have it as an example. We already done that proof, like maybe 2 days ago. But let me write it right there, because usually that's the most popular tool, this one. Well, I don't have my pen. I'm gonna go and get the pen. Oh, I'll plug this one in right away.
Guys, do you guys know if what the difference is between equivalency and an equal sign?
I'm still struggling to figure it out. I asked
feel
him like a class ago, and he was saying like equivalency is applicable to more things, and like there's like an inherent assumption in an equal sign with what you're working with. Like the equals for the remainder thing, there's an assumption that when you use the equal sign, that the remainder will be bounded between 0 and n. But in equivalence, there's no assumption like that. But like I'm still trying to understand it, but that's what he was trying.
Okay.
That's what he said. I don't know.
I'll ask him and maybe we can get him to explain it again.
Yeah.
I think I had taken it as just like it's the result of something whenever you do the equal sign. So when you do like the mod, you would get the actual result instead of equivalency being the same statement.
We've decided that we don't know the difference between equivalency and equal signs.
Oh, me neither. No, just kidding, just kidding. Let me see. No, okay. No problem. I'll write. Let me see. So there, I was gonna put that example, and then we'll talk about that right away. For all A, comma B, comma N, and N in Z with N greater than 1, comma, if A it's equivalent to B mod N, then A square it's equivalent to B square mod N. So that was the example. That's something to practice for the exam. So let me circle it and let me just go and talk about that hard question right there. It actually a philosophical question. What is equivalent and C and what is equal? Okay, let me tell you why it's hard, and then we'll try to talk about it. Because we go to logic. When our friendship just started, we were playing in logic right there, and in logic we had the P or Q, P or Q, P or Q negation, it's equivalent to not P and not Q, right there. And that's in the world of logic. And we are using equivalency right there. But then we can go to the world of sets. And in the world of sets, we get the same idea. A union, we will be proving this a few weeks ago, like on week 12, we'll be proving that A union B complement is equal to A complement intersection B complement. And mathematically, those two ideas are the same. We're talking about the Morgans on their sets and the Morgans and their logic. But now, if you allow me to go to Boolean algebra and change the P's and Q's to ones and zeros and call all the logic that we've done Boolean algebra, the equivalency changes to an equal sign. So in some areas of math, the equivalency is taken to be equal, but the idea of equivalent is that they're equal in some general sense. Let me give you this example. For example, I could have a triangle. I could have that equilateral triangle and then tell you that that equilateral triangle is equivalent to this equilateral triangle. They are not equal because one is larger than the other one. Clearly, they are not equal, but they are equivalent because they have some properties in common right there. So in some sense, they are equal, meaning that their sides are equal and their angles are equal, but the triangles are not equal. So in that sense, I could say, well, these two triangles are equivalent right there. Or we can say that they are similar triangles right there, but we never will say that that is an equality. Okay with that? Okay.
Would they also be equivalent if they were the same size?
Of course. If they could be equal, they're the same size and they're equal and equivalent. But if the size change, they are equivalent right there.
So
yeah,
equal
okay.
signs, when we find that something's equal to something else, we now have the freedom to write whichever one we want. And it's the same
It
thing.
depends. It comes to you, the burden of whoever is working on that field and decided to just call them equivalency first. Can you see what I'm saying? You are tied by the
Oh, I
notation
mean-
of your ancestors.
Sorry, I mean, for an equal sign, when you have an equal sign between two things, like if you say A equals B, then the fact that you know that A equals B means that they're the same thing. You can write the same math problem either way. But equivalency doesn't give you the freedom to write either one.
It's more general. Yes,
Okay.
yes. If you like two sets are equal. So when you have right here and you tell me that the set A is equal to the set B, they better have the same elements. So then both better have 1, 2, and 3 in them right there. Okay with that right there. So when we say equal is one, of course, we'll prove it. One is a subset of the other one, and the other one is a subset of the other one. But like this, if you were to prove that, well, we will prove those things later. But again, it's more constrained inequality. Equivalency is more general right there. Now, if you go and ask ChatGPT to explain what's the difference between equivalency and equal, you see ChatGPT sweating a little bit. At least ChatGPT is going to tell you, good question. And then it will elaborate on that. I'm certain. Let's go and ask right there. So in real time, let's go and ask ChatGPT and it will give some examples right there. So we'll ask for examples. So I'll do it at once. I'll share with you right there. I'll go to chat. Of course, it might start talking in Spanish because I speak Spanish with chat, but it's going to say mostly everything in English. Let's see. So I'll say, chat, could you elaborate right there? No. Could you chat about equality and equivalence, comma, the difference between both, and some examples. And I'm not going to say anything in Spanish because if not, it will go in Spanish right there. So I'm not going to even say gracias. Okay, I'll go. Sure, Che. It calls me Che. I told you. And that's what you were saying, Ansley. They're the same thing. Equivalency, sharing some property. Living in the same class, in the same equivalence class. And then they went to something that we are going to talk about, an equivalence relation. They have to have those properties, the reflexive, symmetric, and transitive. We'll talk about those in chapter 8. And then it went for some examples right there. And it went for set equality. Can you see it's doing, it's pretty cool. It's a pretty cool tool. I mean, we need to utilize it. If you want to show, I mean, it's better than watching some random YouTube video that here is becoming better. This is learning more, is improving daily by everybody working with the language model right there. And look, it keeps going and it goes into programming right there. So, and then we can keep talking and just going to the philosophy of both. But can you see, it's a nice place to start, always. That was a difficult question. You can see, right there. But we need that in mathematics. We need in mathematics the idea to say these two sets are equal. But we need in mathematics the flexibility to say these two objects have, in certain sense, have some similar properties. And then call that equivalency, because the two objects will not be the same on everything, but they will be the same on some sense. Okay with that, as a language needs that power. Yeah. So it's a hard question. It was a hard question. Happiness with that. So always use equivalency for congruences, because they are equivalence classes right there. They're all divisible. Yeah, they're all, let's say mod 3. We have the multiples of 3, the multiples of 3 plus 1, and the multiples of 3 plus 2. So perfect, right there. So in principle, you can learn mathematics on your own with books, of course, but with the help of a language model like this, you can become more abstract. You can just, it's not, now it's more right than wrong. A lot more times it's right than wrong with the correct examples. So it's better than last year, a lot better than last year, the free version. So perfect. Let me go right away to this. Section 9.4.
I have a quick question.
Yes, Milani.
So the last thing that we went over, if A is equivalent to B mod n, then A squared is equivalent to B squared mod n.
Yeah.
Do we have to prove that when we in a test question, or would that statement be what we are proving? Or can we consider it previously proved?
Milani, that could potentially be a question on an exam, right there, or I can make it an immediate homework, but it will be simpler than the last immediate. The last immediate was spicy, right there. So this one is simpler than the last immediate. It could potentially have taken the place, right there, and of course, if I were to do the jot on this one on the side, is not the proof, but only the jot. Well, you are going to be playing with a squared minus b squared, and you are going to factor and write it as a minus b and a plus b, and that's the heart of the proof when you are trying to do that proof. Okay with that? Okay. Perfect. So section 9.4, it's in the chapter in probability, because probability is counting. A lot of probability is counting. That's the very hard part of probability, counting. But it could have been in chapter 4. It's a method of proof. So it's an existential proof. This is what it's called. And it's called, the concept is the pigeonhole principle. Pigeonhole principle. In Spain, they will call it teorema Teorema de las gavetas. Gavetas is what you used to have at the libraries to take a look at those cards, those index cards. In the past, in the libraries, we didn't have computers. We had to go and look at these drawers that you pull, these tiny drawers that they have a bunch of index cards. And you can use the index cards as paper right now, as just to write on them, because they're useless. But that's what it is. Is the pigeonhole is similar to those holes in the library right there that we could put things on it. So here it comes. So we're going to build the mathematics for that, for the pigeonhole principle. So I cannot give you the principle right away. I need to talk about functions. functions right there. Suppose I have a function right here. I have a set right here, the set X. And there is the set Y. Here I could potentially have A, B, C. And there I could have 1, 2, 3, 4. Right there. So A maps to 2, B maps to 3, C maps to 4. So this is a one-to-one function. We have a one-to-one function. So this, let me put it right here on the side. F, the function, is one-to-one. F is one-to-one. Or injective. What does it mean? The definition in computer science is, so the definition of one-to-one in computer science is every element of the codomain gets mapped to at most once. The codomain is the Y. Every element of the set Y of the codomain, every element of the codomain gets mapped to at most once. That's the useful definition, because we have another one that we use in test 1. It was there in test 1, that definition, but it's not useful in this case because we're going to use it for counting. Because look, I take a look at the size of the set X. This is for finite sets. X and Y are finite, not infinite. I take a look at the set of Y. Y is greater than equal to X, or X is less than or equal to Y. Here, X and Y are finite functions, and we want to use it for counting. So for the principle, for the pigeonhole principle, X and Y are finite. So X and Y are not infinite. And the computer scientist, she really wants to get to know the set X. The set X is too complicated. She cannot count that set. It's difficult. It's difficult counting. So then she will construct the set Y that she knows very well. And she will construct the one-to-one function. And now she put an upper bound on the set X. She said, well, the set X is at most Y right there. So you got to know that set. It would have been something very difficult to count right there. Okay with that? Okay. Well, something very difficult to count could be all the different ways I can buy 12 sodas when I have 5 brands. Can you see what I'm saying? I have 5 brands and I need to buy 12 sodas because I have an honors class that is going to have a potluck right there. So how many different ways I can purchase those 12 sodas under 5 different brands? So all of them could be Coke. All of them could be Tab. Doesn't exist Tab anymore. It went out of, they took it out, but it was a soda right there from the 80s and so on. That's difficult to count. So she will construct the set Y. She will construct a one-to-one function and she will put an upper bound. Okay. Next, an onto function. There. Onto, an onto function. I'll put it right here. F is onto. Or surjective. So now every element of the codomain every element of the set Y every element of the codomain gets mapped to well, that one was at most once. What do you think is this one?
At least once?
At least once. You cannot have, and so here the range and the codomain are equal. Everybody gets mapped to right there. So you get everybody gets mapped to in the codomain. Can you see? I didn't have like a 3 hanging like that. So that will kill the idea of onto. Perfect. So every element of the codomain gets mapped to at most once. So the size of X as a finite set is greater than equal to the size of Y.
Wait, isn't it at least once?
Oh, I'm sorry. At least once. Yes. I was thinking at least once and I wrote at most once. Perfect. Thank you. At least once. Right there. So yeah. So and then can you see? You have a set that is difficult to count, set X. It's complicated. And then you create an onto function. So if you create an onto function, you put a lower bound on that set right there. On the previous one, we put an upper bound on the set X. And now we put a lower bound on the set X and we have it trapped between two values. We really know very well the set Y. Usually the set Y could be a set of ones and zeros that the computer scientists know very well. Yeah. Okay. So perfect. And now we get the next one. One-to-one and onto, or it's called a one-to-one correspondence, or it's called bijective. It's both right there. So the set will be equal in size right there. This is X. There is Y. And there is the ABC 1, 2, 3. A maps to 1, B maps to 3, C maps to 2. And the size of X is equal to the size of Y right there. And we have F is 1-to-1 and onto. And that is called bijective. Bijective. In Spanish will be bijectiva. And what will be in French? Bijective. Bijective. Okay. So perfect. So there, F is 1-to-1 and onto. And also we say a 1-to-1 correspondence. If somebody says a 1-to-1 correspondence is not only 1-to-1, it's 1-to-1 and onto. That's confusing sometimes. It's a 1-to-1 correspondence. So here it comes the definition. Every element of the codomain gets mapped to? Well, this is like the Goldilocks, Remember, we have at least ones. We have at most ones. So for 1 to 1 and on to, we get
Exactly.
exactly. Oh, and that's exactly for both. Exactly for what you said, and is exactly. Okay, with that, it's a double meaning right there. Okay, yes, exactly once. Gets mapped to exactly once. So perfect. A computer scientist, if she gets her hand on the function and the function is 1 to 1 and on to, it's a 1 to 1 correspondence. The sets have equal, so she counted it to perfection. That set X that was recalcitrant. All the number of 12 sodas that you can get by choosing from 5 different brands is she would have gotten the exact number right there if she would have mapped it with the 1 to 1 correspondence to some set that she knows. Right there. Happiness with that. Perfect, perfect. Now comes the pigeonhole principle. The pigeonhole principle says, suppose right here, you have some pigeons. I can draw the pigeons a lot better, believe me, but I cannot, no, I'm not sure. Yeah. So there I have 4 pigeons. That's the X. So the domain, finite set of pigeons. And there you have the holes. Right there. And you have a function, F. And you have more pigeons than whole. That's the hypothesis. Finite sets and more pigeons than holes. You have the existence of one hole that will have 2 pigeons. The first time I saw this, I thought I was going to miss class. I'm like, did I come for this? Right there. But it's a very powerful tool. You'll be surprised. A lot of my colleagues have used this tool in their PhD thesis. Right there. One of my colleagues is across my office. I went and I told him, look, I'm going to go and teach the pigeonhole principle. And he told me, I use it in my thesis right there. So it's super powerful right there. So I need to write it in 1 minute and then we'll prove it next time. I'll write it super fast and we have super freedom. Let X and Y be finite sets. If the set X is greater, strictly greater, the number of pigeons, greater than the number of holes, then for all functions that you can write, for all functions that you could author from the size from X to Y, comma, there are two elements. When I say 2 elements, I mean 2 or more. There are 2 elements in X that map to 1 and only 1 Y in Y. right there. We'll use this concept. We'll prove it. It's easy to prove. We'll prove it my way. That is really fast. And some students sometimes don't like it. And then we'll take a look at Susanna's way. That is very, very long, but it's nice also. It's nice the way she proved it. And then we'll use it to prove other problems. For example, that there exists, it's an existential proof. There are two austonites, two non-bold austonites that have the same number of hairs in their head. I never show them to you, but they must exist. Pretty cool. Right there. So, super freedom. Enjoy the weekend.
Thank you. Bye.
Bye.
Ciao.